In the silence between stars, a generation ship carries not just people, but entire lifetimes. Children are born, elders fade, and the destination may still be centuries away. But behind the dream of interstellar travel lies a darker question. What happens when a spacecraft becomes the only world humanity has left? This is Generation Ships Explained, the dark side of interstellar travel. If this journey interests you, please like the video and subscribe for more quiet documentaries about space, science and the future, far beyond the orbit of Neptune, beyond the drifting bodies of the Kuiper Belt, beyond the weak pull of the Sun on scattered comets. Interstellar space begins as an almost empty region between stars. A generation ship enters this region slowly by human standards and rapidly by the standards of ordinary spacecraft. The vessel moves for centuries or longer through darkness that contains no air, almost no matter, and very little warmth. The stars remain separated by distances so large that even light requires years to travel from one system to another. The nearest known star beyond the Sun, Proxima Centauri, lies more than 4 light-years away. A light-year is the distance light crosses in 1 year through empty space. Even at speeds far beyond those reached by present-day human spacecraft, a journey between stars remains longer than a single human lifetime. The outer environment surrounding such a vessel appears still. Observations from telescopes and deep space probes show no clouds, storms, or visible currents between nearby stars. Yet the stillness hides constant motion. The solar system itself circles the center of the Milky Way galaxy at hundreds of thousands of kilometers per hour. Nearby stars drift through space under the pull of gravity from countless distant masses. Interstellar space is not fixed or frozen. It changes slowly over immense periods of time. A generation ship leaves behind the strong influence of the Sun. Near Earth, sunlight dominates nearly every physical process. Solar radiation warms spacecraft surfaces. Solar wind, a stream of charged particles flowing outward from the Sun, shapes the magnetic environment around planets. Communication signals travel through a region monitored by human instruments and supported by networks of antennas. Far beyond the outer planets, these familiar conditions weaken. Sunlight fades until it becomes only a bright star among many others. At the distance of Neptune, sunlight is already hundreds of times weaker than at Earth. Deeper into interstellar space, the Sun no longer illuminates the ship in any meaningful way. Darkness becomes the dominant condition. The ship depends entirely on internal power systems for heat, light, air circulation, farming, and computation. Every surface exposed to space loses heat through thermal radiation. Thermal radiation is the transfer of energy as invisible electromagnetic waves. Without constant energy production, the vessel slowly cools toward the natural background temperature of deep space, only a few degrees above absolute zero. Absolute zero marks the coldest possible temperature allowed by physics, where atomic motion reaches its minimum state. The stars visible from the outer hull no longer resemble the sky seen from Earth. There is no atmosphere to scatter light, no sunrise or sunset, and no familiar horizon. The Milky Way stretches across the darkness as a pale band formed by billions of distant stars. Some stars appear brighter as the ship gradually changes position over centuries. Others dim or vanish behind drifting dust clouds. The changes occur so slowly that generations aboard the vessel may not notice them directly. Records stored in observatories' navigation archives reveal the motion only when compared across long spans of time. Interstellar space contains enormous emptiness. On Earth, Even the highest vacuum chambers still contain trillions of particles in a small volume. Between stars, the average density falls to only a few atoms per cubic centimetre. A cubic centimetre is a space roughly equal to the size of a small sugar cube. Much of interstellar space contains even less matter than this. Hydrogen atoms dominate the region because hydrogen is the simplest and most common element in the universe. Helium follows in smaller amounts. Tiny grains of dust drift between them. Despite the emptiness, interstellar space cannot be treated as perfectly empty. Over decades and centuries, even rare particles accumulate effects. Every exposed surface encounters slow bombardment from atoms, dust grains, and radiation. Electronic systems experience gradual degradation. Structural materials weaken at microscopic scales. Protective layers erode molecule by molecule. The long duration of the voyage transforms small hazards into serious engineering problems. Distance itself becomes one of the greatest conditions shaping life aboard the vessel. Signals sent from Earth travel at the speed of light, the fastest speed known in nature. Even so, messages require years to cross the gap between stars. Communication with Earth becomes increasingly delayed as the ship moves farther away. A reply to a transmission may arrive decades after the original message was sent. For many aboard the vessel, Earth exists only as archived history rather than a living society. Political systems, languages, and cultures on Earth may transform completely during the voyage. Observations indicate that no realistic technology presently known can remove this communication delay because information cannot travel faster than light, according to established physical laws. The ship itself becomes an isolated world moving through a region with no possibility of rescue. Modern spacecraft near Earth can often rely on support from mission control, supply launches, or nearby stations. A generation ship cannot depend on such assistance. Every tool, medical system, seed bank, industrial process, and scientific archive must survive within the vessel or be reproduced aboard it. Failure of critical systems threatens not only a crew, but entire future generations who have never seen another world outside the ship. Outside the hull, gravity remains weak but never absent. Every star, planet, and galaxy exerts gravitational pull across space. Gravity is the attraction between masses. In interstellar regions far from large bodies, these forces nearly balance, allowing the vessel to travel along predictable paths. Yet even tiny gravitational influences slowly alter trajectories over centuries. Navigation systems must constantly measure the ship's position against distant stars and other astronomical markers. The silence of interstellar space is also unlike silence on Earth. Sound requires matter such as air or water to travel. The vacuum outside the hull carries no sound at all. Impacts, vibrations, and machinery noises remain trapped within the vessel structure. Beyond it lies complete acoustic emptiness, broken only by invisible radiation and drifting particles crossing the darkness. As the ship advances farther from the solar system, the sun gradually loses its role as the central object in the sky. Its light shrinks into a distant point among countless others. The familiar arrangement of constellations slowly changes shape because the vessel moves into a new position within the galaxy. Over centuries, the sky itself becomes unfamiliar. Navigation maps require continual adjustment as stars shift relative to one another. The outer region of the voyage therefore consists not of dramatic events, but of extreme isolation maintained over extraordinary time. The environment appears empty, cold, and calm. Yet beneath the calm lies a continuous interaction between matter, radiation, energy, and distance. every process aboard the vessel exists in response to this immense surrounding void. The interstellar medium fills the region between stars with matter so thin that it seems almost absent. Yet observations show that it forms a real part of the galaxy. It is not a single substance. It is a mixture of gas, dust, magnetic fields, and radiation spread through vast space. Most of it cannot be seen directly by the eye. Astronomers detect it through the way it absorbs starlight, emits faint signals, scatters radiation, and shapes the birth and death of stars. A generation ship crossing this medium does not move through a perfect void. It passes through an extremely thin material environment that slowly touches every outer surface. Hydrogen is the main gas in this region. Some hydrogen exists as separate atoms, each made of one proton and one electron. Some exists as molecules, where two hydrogen atoms are bound together. Some is ionized, meaning the electron has been separated from the atom, leaving a charged particle. These forms are not evenly spread. Interstellar space contains warmer, thinner regions and colder, denser clouds. The ship may spend long periods in diffuse gas where particles are very rare. It may also pass near or through regions where dust and gas are more concentrated. Although known routes between nearby stars can be studied in advance with telescopes, the gas is thin by any human measure. Near sea level on Earth, air contains an enormous number of molecules in every breath. In interstellar space, a comparable volume may contain only a few atoms, or fewer. This low density means there is no wind in the ordinary sense. There is no pressure against the hull like air against an aircraft. Still, motion changes the meaning of thinness. A ship travelling at a significant fraction of the speed of light meets particles with high relative energy. Each atom becomes a tiny impact. Individually, most atoms do little. Together, over years and centuries, they create a persistent stream of collisions. Interstellar dust is less common than gas, but it is more dangerous to a moving vessel. Dust grains are small solid particles made from elements such as carbon, silicon, oxygen, magnesium, and iron, often bound into minerals or icy compounds. Many grains are smaller than bacteria. Some are larger, though still tiny by ordinary standards. These grains form in the outer layers of aging stars, in supernova debris, and in cold clouds where atoms stick together. They drift through the galaxy, shaped by gravity, radiation, and magnetic forces. Dust reveals itself by dimming and reddening starlight. Shorter blue wavelengths scatter more easily than longer red wavelengths, so light passing through dust clouds can arrive redder than it began. In dense clouds, dust blocks visible light so strongly that stars behind it seem to vanish. Infrared telescopes, which observe heat radiation, show these clouds more clearly. Observations indicate that interstellar dust is uneven and complex. Its exact grain sizes, shapes, and compositions vary from one region to another, and some details remain uncertain. A generation ship must treat this uneven medium as a changing external condition. The vessel moves through zones where the density may rise or fall. The changes are not usually sudden like storms on Earth. They are spread across astronomical distances. Yet for a ship that must survive a long journey, even gradual changes matter. More gas means more particle impacts. More dust means greater risk of surface erosion and damage. Stronger magnetic fields affect charged particles and can influence shielding designs. Magnetic fields thread through the interstellar medium. A magnetic field is an invisible region where charged particles experience forces. These galactic fields are weak compared with magnets used in laboratories, but they extend over enormous distances. They guide ionized gas and cosmic rays along curved paths. They also help shape large clouds and influence how matter moves through the galaxy. For a ship, these fields are not usually strong enough to push the hull directly in a significant way. Their importance lies more in the way they affect charged particles and the surrounding space environment. The interstellar medium also contains radiation from many sources. Starlight travels through it from nearby and distant stars. Ultraviolet radiation, which has more energy than visible light, can ionize atoms and alter molecules on dust grains. X-rays and gamma rays come from hotter and more energetic events, including stellar remnants and violent regions near compact objects. The cosmic microwave background, a faint radiation left from the early universe, passes through all directions as a cold glow. This radiation is weak, but it forms part of the physical background of deep space. The medium is also changed by stellar explosions. Supernovae, the explosions of certain dying stars, send shock waves through interstellar gas. A shock wave is a moving disturbance that compresses and heats material. These events enrich space with heavier elements made inside stars. They also carve large bubbles of hot, thin gas. The solar system is believed to sit within or near a region of unusually low density shaped by past stellar activity, often called the local bubble. The exact structure of nearby interstellar space continues to be studied, and maps improve as new observations become available. Within such a region, a ship's path is not simply a line through darkness. It is a line through a lightly structured galactic environment. The densities are low, but they are measurable. The gas has temperatures, although temperature in such thin matter does not feel like warmth, because there are so few particles to transfer heat. Some regions contain gas at thousands or millions of degrees Celsius, in the sense that individual particles move very fast. Yet the ship would not be heated like an object inside hot air, because the particles are too sparse. This difference between particle energy and experienced heat is important. Temperature describes the average motion of particles. Heat transfer depends on how many particles strike a surface and how much energy they deliver. In interstellar space, very hot gas can still transfer little heat because there is so little gas. Radiation and internal systems remain more important for the ship's thermal state than ordinary contact with external matter. The interstellar medium also affects observation. Dust and gas can block, scatter, or shift signals from stars used for navigation. Charged particles can disturb sensitive detectors. Radiation can create noise in instruments. The ship's observatories must separate true astronomical signals from local effects caused by particles striking sensors or by material around the hull. Over long times, dust deposits and surface changes can reduce the clarity of exposed instruments unless they are protected, cleaned, or replaced. The dark side of this medium lies in its quiet persistence. It does not present a wall, an ocean, or a storm in the familiar sense. It offers almost nothing, and that almost nothing lasts without pause. Gas atoms arrive one by one. Dust grains appear rarely, then suddenly matter at high speed. Magnetic fields bend charged particles across invisible lines. Radiation passes through exposed materials. The ship remains surrounded by a thin, ancient mixture left by stars, carried by the galaxy, and spread across the distance between suns. Cosmic radiation reaches a generation ship from many directions, moving through interstellar space as particles with high energy. This radiation is not the same as ordinary light, although light is also a form of radiation. In this region, the main concern is the stream of charged particles that can pass through matter, strike atoms inside materials, and alter living cells. Some particles come from the sun, but their influence fades with distance, farther from the solar system. Galactic cosmic rays become more important. Galactic cosmic rays are high-energy particles that travel through the galaxy, often from violent astrophysical events such as supernova remnants. Their exact paths are shaped by magnetic fields, so they do not point neatly back to their sources. Most galactic cosmic rays are protons, which are the positively charged centers of hydrogen atoms. A smaller share consists of helium nuclei, and a still smaller share contains heavier atomic nuclei. These heavier particles are less common, but they can be especially damaging because they carry more charge and can deposit energy densely along their paths. Electrons and other particles also contribute. The radiation field changes with time and location, but it is present throughout deep space. Observations from spacecraft and particle detectors show that outside the protective influence of planets and strong local magnetic fields, exposure becomes a major risk for long-duration travel. Near Earth, the planet's magnetic field and atmosphere reduce radiation at the surface. The magnetic field diverts many charged particles, and the atmosphere absorbs or breaks up many that enter. A generation ship has neither a planet-sized magnetic shield nor a thick natural atmosphere around it. Its protection must come from design. Shielding materials, internal layout, and operational choices determine how much radiation reaches the people and systems inside. When a high-energy particle enters matter, it can collide with atoms and molecules. It may knock electrons loose, creating ionization. Ionization is the removal of electrons from atoms or molecules, leaving charged pieces behind. In living tissue, ionization can damage DNA, proteins, membranes, and other structures. Cells have repair systems, and many small injuries can be corrected. Some injuries remain. Over long exposure, unrepaired damage can increase the risk of cancer, cataracts, nervous system effects, cardiovascular harm, and other health problems. The full risk for exposure across generations in deep space remains uncertain because human experience beyond Earth's magnetic protection is limited. Radiation also matters before birth and during growth. Embryos, children, and adolescents have dividing cells that can be sensitive to damage. A generation ship contains a complete human life cycle. Not only trained adults on a mission, medical planning must account for pregnancy, childhood development, inherited risk, and lifelong exposure. Scientific knowledge from medicine, radiation biology, and astronaut health offers guidance, but it does not yet provide complete certainty for continuous exposure across centuries. The dose received by a person depends on the energy of the particles, the kind of particles, the shielding around them, and the time spent in exposed areas. A dose is a measure of radiation energy absorbed by matter. For human health, the biological effect also depends on how strongly that radiation damages tissue. Heavy charge particles can cause dense tracts of ionization that are harder for cells to repair than damage from many lower energy forms of radiation. This makes simple comparisons difficult. Shielding is not as straightforward as adding thicker walls. Dense materials can stop some particles well, but high-energy cosmic rays may strike the shielding and produce secondary radiation. Secondary radiation consists of new particles created when incoming particles collide with atoms in the shield. These new particles can continue inward and add to the dose. Materials rich in hydrogen, such as water or certain plastics, are often useful because their light atomic nuclei can reduce some secondary effects. Water, food stores, waste tanks, and fuel can be arranged around living areas to add protection. This approach uses mass already needed by the ship. The outer sections of the vessel receive the greatest exposure. Living quarters, medical rooms, nurseries, and long-term archives are better placed deeper within protected regions. A storm shelter may also exist inside the ship, designed as an area with extra shielding. In the solar system, such shelters are often discussed for solar particle events, which are burst from the sun. In interstellar space, solar events from the sun fade, but other energetic events in the galaxy remain part of the background. The ship's deeper protected areas reduce exposure during periods when measurements show increased particle activity. Radiation affects machines as well as bodies. High-energy particles can pass through electronic circuits and deposit charge in small components. A single particle strike can change a bit in memory, disturb a sensor, or damage a device. This is called a single event effect. Over time, accumulated radiation can degrade materials, cloud optics, weaken polymers, and alter semiconductors. A generation ship depends on electronics for navigation, climate control, medicine, agriculture, manufacturing, and records. Its systems must tolerate radiation through shielding, redundancy, error correction, replacement parts, and designs that fail safely. Radiation also changes materials at microscopic scales. It can break chemical bonds, displace atoms in crystal structures, and create defects. Metals, ceramics, glass, and polymers respond in different ways. Some become brittle, some swell, some lose transparency, some change electrical behavior. These changes are often slow, but the voyage is long enough for slow damage to matter. Regular inspection cannot rely only on visible cracks or surface wear. Instruments must measure hidden changes before they reach dangerous levels. The ship's own structure may become slightly radioactive when particles strike nuclei and create unstable isotopes. This process is called activation. In many cases, activation is limited, but it must be understood for maintenance and waste handling. Parts removed from exposed regions may require controlled storage. Workers repairing outer systems need protection not only from present radiation, but also from materials changed by past exposure. Cosmic radiation is difficult because it is continuous and partly unavoidable. It cannot be turned off. It does not arrive as a single event that ends cleanly. It passes through space at all times, varying with the galactic environment and with the shielding around the ship. The dark side of this region is not only the harm caused by rare intense events, it is the steady addition of risk to every body, every circuit, every stored seed, and every material surface across time. The known science provides clear warnings. Space beyond planets is a radiation environment unlike Earth's surface. Shielding helps, but shielding has mass, and mass is costly to accelerate. Biological repair helps, but repair is incomplete. Electronics can be hardened, but no system lasts forever without maintenance. Observations indicate that radiation is one of the central limits on long human travel beyond the solar system. It remains uncertain how best to protect a closed society from it across many generations, because no human community has ever lived for such lengths of time in deep interstellar space. Relativistic dust impacts begin with matter almost too small to notice. A grain of dust between stars may be narrower than a human hair, smaller than a cell, or smaller still. In ordinary life, such a particle drifts harmlessly through air or settles on a surface. In interstellar travel, speed changes its meaning. When a generation ship moves at a significant fraction of the speed of light, the energy of impact rises sharply. The dust grain remains tiny, but its collision with the ship becomes a concentrated release of heat, shock, radiation, and fragmented material. Relativistic means that motion is fast enough for the effects described by Einstein's theory of relativity to become important. A generation ship may not reach speeds close to the speed of light by the standards of advanced physics, but even a small fraction of that speed is far beyond normal spacecraft motion. At such speeds, the difference between a speck and a projectile becomes less clear. The danger does not come from the mass alone. It comes from mass combined with extreme velocity. Interstellar dust is uneven. Most grains are very small, and larger grains are rare. Observations of starlight, spacecraft dust detectors, and samples of cosmic dust suggest a broad range of sizes and compositions. The smallest grains may contain only clusters of atoms or molecules. Larger grains may include silicates, carbon-rich material, metal compounds, or ice. Their shapes are irregular, not smooth spheres. Some grains may be porous, like fragile stone. Others may be compact. The exact distribution of larger grains in nearby interstellar space remains uncertain, and this uncertainty matters because larger grains, even if rare, carry much greater impact energy. A ship crossing this region does not meet dust as a cloud visible ahead. The grains are too sparse and too small to form an obvious obstacle. Most of space remains empty, yet the ship sweeps through a vast volume over time. Its forward-facing area gathers risk in proportion to its size, speed, and duration of travel. A broad vessel travelling for centuries meets more particles than a small probe travelling briefly. The outer front of the ship becomes a collection surface for the hidden material of interstellar space. When a dust grain strikes at high speed, the first event occurs at the surface. The grain and a small region of the shield can vaporize or ionize almost instantly. Vaporization turns solid material into gas. Ionization strips electrons from atoms and creates charged particles. The impact can form a tiny plasma, a hot mixture of charged matter, that expands away from the strike point. This expansion sends a shock into the surrounding material. A shock is a sudden compression moving through matter. In the shield, the shock can crack, melt, spool, or eject fragments. Spallation is a process in which material breaks away from the back or inside of a surface after a strong impact wave passes through it. In a thin shield, a dust impact may not simply make a small crater. It may send fragments inward. These fragments can become secondary projectiles inside the protective layers. A single grain outside can become a spray of material moving through the shield. The design must prevent that spray from reaching pressure vessels, pipes, cables, radiators, sensors, or living areas. One common protective idea is a Whipple shield. This is a space shield in which a thin outer layer breaks up an incoming particle before the fragments reach a deeper wall. The space between layers allows the debris cloud to spread out, lowering the energy at any one point. This approach is used in spacecraft protection against micrometeoroids and orbital debris. For interstellar travel at much higher speeds, the principle remains useful, but the required scale becomes more demanding. Higher velocity produces more violent impacts and more energetic fragments. Multiple layers, sacrificial materials, and large separation distances may be needed. The front of the ship faces the greatest danger because it meets the interstellar medium head-on. Side surfaces also receive impacts, but the relative speed and particle direction make the forward direction more severe. The bow of a generation ship may need to function less like a simple wall and more like a long protective system. It may include outer dust screens, replaceable plates, thick shields, stored water, structural gaps, and sensor fields. Each layer has a purpose. Some layers break grains apart, some absorb heat, some trap fragments, some protect the deeper habitat from the last remaining particles. Detection is difficult. A grain large enough to threaten the ship may still be too small and too dark to see from a great distance. Telescopes can map larger clouds and estimate average dust density along a route, but they cannot locate every dangerous grain. Radar and laser systems may detect particles close to the ship, only if the particles are large enough and if there is enough time to respond. At very high speed, response time becomes short. Deflecting or destroying a grain ahead of impact requires energy, precision, and rapid control. It remains uncertain how effective active detection and clearing systems can be across centuries without constant maintenance. Dust impacts also produce radiation and electromagnetic disturbance. The hot plasma from a strike can emit light, ultraviolet radiation, X-rays, and charged particles. It can create electrical pulses in nearby conductors. Sensors on the outer hull may register flashes, noise, and sudden currents. Repeated impacts can confuse instruments if systems are not designed to distinguish damage signals from environmental measurements. Communication antennas and exposed observatories are especially vulnerable because they require clear lines of sight and cannot always hide behind thick shielding. Surface erosion accumulates. Most impacts are too small to be catastrophic, but each removes or changes a little material. The forward shield becomes pitted, roughened, and chemically altered. Craters overlap. Thin coatings lose their designed properties. Reflective surfaces darken. Thermal surfaces change how they absorb and emit radiation. Over time, the shield no longer behaves like new material. A generation ship must either carry enough protective mass to tolerate this loss or possess the ability to inspect, repair, and replace outer layers from within its own resources. Repairs in this region are difficult because the damaged area is also the area most exposed to incoming particles. Robotic systems may be safer than human workers for outer maintenance. Machines can move across the shield, weld, deposit material, replace tiles, and measure hidden cracks. Yet the machines also suffer impacts and radiation. Their tracks, joints, cameras, and tools require protection. If repair systems fail, the ship loses part of its ability to preserve its own skin. The most severe concern is the rare larger particle. Scholarly studies of interstellar dust often emphasize uncertainty in the abundance of grains large enough to cause major damage. A particle only a small fraction of a millimeter across can carry serious energy at interstellar speeds. A larger grain can be mission-threatening if it reaches critical structures. The rarity of such particles does not remove the danger, because the travel time is long and the path length is immense. The dark side of relativistic dust is this imbalance between size and consequence. The threat is not visible as an approaching field of rocks. It is carried by grains that may be smaller than dust on a windowsill. The ship crosses emptiness, yet emptiness contains enough matter to strike, heat, fracture, and erode. In this region, the smallest solids of the galaxy become a long test of shielding, patience, repair, and uncertainty. Navigation across starless distance begins with the loss of nearby markers. Around Earth, a spacecraft can compare its position with planets, moons, ground stations, and known radio signals. In interstellar space, these reference points fall far behind. The solar system shrinks into a distant source of light and radio memory. The destination star remains a point ahead, sometimes hidden among other stars that share the same field of view. The ship travels through a region where distance is measured less by landmarks than by angles, time, velocity, and the slow geometry of the galaxy. The basic problem is simple in outline and difficult in practice. The vessel must know where it is, how fast it is moving, where the destination will be when the ship arrives, and how small corrections change the final path. Stars are not fixed. Each one moves through the Milky Way under the pull of gravity. The target star does not wait in place. It follows its own orbit, and its planets move around it. A generation ship must aim not only toward where a star appears, but toward where the system will be after many decades or centuries of travel. Astronomers measure stellar positions with high precision using astrometry, the study of star locations and motions. Space observatories have mapped the positions, distances, and movements of many stars. These measurements provide the starting map for a voyage. Yet any map has limits. Small errors in the measured motion of a distant star can become large over long travel times. A tiny uncertainty in velocity or direction can grow into a wide miss after light years. Navigation therefore depends on repeated measurement, not on a single launch calculation. The ship observes the sky around it. Cameras, telescopes, spectrometers, and timing instruments compare star patterns with stored catalogues. A spectrometer separates light into colours, revealing motion, temperature, and composition. The apparent positions of stars shift as the vessel moves. This shift is called parallax. Parallax is the change in apparent position of an object when viewed from different places. For a ship moving far from the solar system, parallax becomes a useful tool because the baseline or viewing separation grows over time. The sky slowly changes in a measurable way, allowing the ship to refine its location. Pulsars may also help. A pulsar is a rapidly rotating neutron star that sends beams of radiation into space. Some pulsars produce pulses with extremely regular timing. Spacecraft navigation using pulsars has been studied because these natural signals can act like distant clocks. A generation ship could compare pulse arrival times from several pulsars to estimate position. This method is promising in principle, but it depends on sensitive instruments, stable timing, and accurate models of the pulsars themselves. Pulsars can have timing irregularities, and interstellar material can slightly delay or alter signals. The method is useful, but not perfect. Timekeeping becomes central. Position and velocity are linked to time. A ship must know when observations occur, how long engines have fired, how much acceleration has been applied, and how signals have shifted. Atomic clocks can keep very stable time by using the regular behavior of atoms. Over centuries, even very stable clocks require comparison, redundancy, and correction. No single clock can be trusted forever. The navigation system needs many clocks, cross-checking one another, with records of drift and failure. The ship's motion is also known through inertial measurement. Inertial instruments detect acceleration and rotation. They measure how the ship changes its motion from within. These instruments do not require outside signals, but their errors accumulate. A tiny bias in an accelerometer can produce a large position error over time. Inertial navigation is therefore combined with astronomical observations. Internal instruments describe short-term changes. The stars correct long-term drift. Course corrections are costly. A small change in direction at high speed may require large amounts of energy or propellant. If the ship uses rockets, propellant must be carried, manufactured, or collected. If it uses sails, beams, magnetic systems, or other propulsion concepts, the correction depends on the available technology and surrounding conditions. The navigation region is therefore also an energy region. The best correction is often the one made early. when a small adjustment can grow into the desired path over distance. Late corrections may be harder because there is less time for the change to take effect. Uncertainty in the destination adds difficulty. Even if the target star is well measured, planets around it may be harder to predict across long times. Known planets have orbits that can be calculated, but gravitational interactions and measurement limits introduce uncertainty. Smaller bodies, dust belts, comets, and debris may be poorly known. The ship can refine observations as it approaches, but during most of the voyage, the destination remains distant and faint. Navigation toward a star is more certain than navigation toward a specific safe orbit or landing world. The ship must also avoid relying on Earth. Messages from Earth become delayed by years and then longer. Earth-based observatories may continue to send improved star maps, but those updates arrive slowly. They may also become irrelevant if the ship's own position and local observations differ from assumptions made far behind. Navigation becomes a local responsibility. The vessel carries not only passengers, but also the authority to decide its path. Autonomous decision-making introduces another layer. Software must identify errors, compare models, and choose corrections. Human crews may review decisions, but no single generation can understand every inherited system in full detail unless education and records remain strong. A wrong update, corrupted catalogue, or misunderstood instrument fault can shift the ship away from its intended path. Navigation is therefore not only a technical problem, it is a problem of preserving knowledge accurately across time. The starfield itself changes slowly enough to seem calm, but fast enough to matter across centuries. Nearby stars show the greatest apparent motion. Distant stars form a more stable background. The ship uses both. It measures bright nearby stars for position, and faint distant objects for orientation. Galaxies beyond the Milky Way may serve as very distant reference points, because their apparent motions are extremely small over human timescales. Yet even these signals are faint and require sensitive instruments. Dust, radiation, and impacts can degrade navigation sensors. A telescope lens can darken, a detector can accumulate radiation damage, a protective cover can become pitted. If the ship cannot maintain clear instruments, its knowledge of position weakens. Backup sensors must be placed in protected locations and exposed only when needed. Calibration sources inside the ship help test instruments, but they cannot replace the sky. Navigation finally depends on seeing the universe accurately enough. The dark side of interstellar navigation is not dramatic confusion, but the slow growth of small errors. A fraction of a degree, a minor timing drift, a damaged sensor, or an outdated star model can become a vast miss when carried across light years. The ship travels through a region with no roads, no beacons placed by earlier travelers, and no nearby repair ports. Its path exists as a maintained calculation, renewed again and again by observation, across starless distance. Survival depends on knowing location with humility, patience, and repeated correction. The outer hull is the first solid boundary between the generation ship and interstellar space. It is not only a shell, it is a layered system that receives radiation, dust, temperature changes, mechanical stress, and the long pressure of time. From the outside, it may seem like a single surface facing darkness. In engineering terms, it becomes a protective landscape made of shields, panels, seams, sensors, repair tracks, and sacrificial material. Every part of it exists because the region beyond it cannot support life and cannot forgive exposed weakness. The hull must separate an inner world from vacuum. Vacuum is space with extremely little matter and pressure. Inside the vessel, air presses outward against walls, windows, seals, and hatches. Outside, almost nothing presses back. This pressure difference creates constant stress. On Earth, pressure vessels are common in submarines, aircraft, laboratories, and space stations, but a generation ship must preserve pressure over far longer times. Small leaks that would be manageable during a short mission become serious when the vessel must remain habitable for centuries. The outermost layers are not likely to be the same as the pressure wall. A direct pressure wall exposed to interstellar dust and radiation would place too much responsibility on one layer. A safer design separates functions. The outer layers absorb impacts and radiation. Intermediate spaces allow fragments to spread and energy to dissipate. Deeper layers maintain pressure and structural integrity. This arrangement accepts that the outer skin may be damaged many times while the living volume remains protected. Materials must be chosen for more than strength. Metals can carry loads and resist many forms of damage, but they conduct heat and can suffer fatigue, corrosion in internal environments, and radiation effects. Ceramics can tolerate high temperatures and erosion, but may be brittle. Polymers can be useful in certain shields and seals, especially hydrogen-rich materials that help reduce some radiation effects, but they may degrade under radiation and ultraviolet exposure. Composites combine materials to balance strength, mass, and protection, but their long-term behavior under deep space radiation and repeated impact must be carefully understood. Fatigue is one quiet danger. Fatigue means the weakening of a material under repeated stress. A hull may expand and contract as temperatures shift. Rotating sections may create cyclic loads. Docking systems, maintenance arms, pumps, and internal machinery may send vibrations through structures. Each cycle can be small. Across many years, small cycles can produce cracks. These cracks may begin at bolt holes, welds, sharp corners, manufacturing flaws, or impact scars. Inspection systems must look for changes too small for the eye to see. Temperature across the hull is uneven. Surfaces facing deep space radiate heat away. Surfaces near internal systems may remain warm. Radiators may be deliberately hot so they can release waste heat. Shielded areas may be cold. This uneven heating causes expansion in some parts and contraction in others. The result is thermal stress. A design that works during a brief test may behave differently after thousands of heating and cooling cycles. The hull must allow movement without tearing seals or misaligning structures. Seals are especially important. A large ship contains many joints, access ports, service panels, instrument mounts, and pathways for cables or pipes. Every opening through a pressure boundary is a possible weakness. Gaskets and flexible seals can age. Metals can creep slowly under stress. Creep is gradual deformation under a sustained load. Polymers can harden, crack, or lose elasticity. A generation ship cannot rely on original seals lasting unchanged for the entire voyage. It must replace, rework, or redesign them from onboard resources. The outer hull also protects against charged particles and secondary radiation. Some shielding may be built into the structural mass. Water tanks, fuel stores, soil beds, or waste processing areas can sit behind hull layers where their mass adds protection. This makes the hull part of a larger arrangement rather than an isolated wall. The outer structure, storage zones, maintenance corridors, and living regions all contribute to the radiation environment inside. The safest spaces are likely to be deep within the vessel, where many layers stand between life and open space. Micrometeoroid and dust shielding require surfaces that can be sacrificed. The ship's forward shield may lose material steadily. Side and rear surfaces may suffer less, but they are not untouched. The hull needs ways to measure erosion and identify weak zones. Embedded sensors can detect impacts by vibration, light flashes, electrical pulses, or acoustic waves through solid material. Acoustic here refers to mechanical waves inside the material, not sound travelling through vacuum. These signals help map where damage occurs and how severe it may be. Repair is not a temporary support function. It is part of the hull's design. Robotic systems may move along exterior rails or crawl across surfaces. Some may carry replacement panels. Others may deposit metal, ceramic, or composite material in thin layers. Additive manufacturing, the process of building parts layer by layer, may allow the ship to produce certain replacement shapes, yet manufacturing in deep space is limited by feedstock, energy, precision, and quality control. A repaired hull section must be tested, not merely patched. Inspection must reach hidden layers. Damage can occur beneath a surface that still looks intact. Instruments using ultrasound, electromagnetic testing, radiation imaging, or strain measurements can reveal flaws. Ultrasound uses high-frequency vibrations inside materials. Electromagnetic testing uses fields and currents to sense cracks or changes. These methods are known on Earth, but aboard a generation ship they must remain reliable without a planetary industrial base behind them. Calibration standards, spare sensors, trained technicians, and clear records become part of the hull's survival. The hull also faces chemical change from within. The interior side touches air, moisture, cleaning agents, microbes, and human activity. Corrosion does not require rain or oceans. It can occur wherever materials react with their environment. Even a controlled atmosphere contains oxygen, water vapor, and trace chemicals. Local leaks, condensation, waste residues, or biological films can attack surfaces. The dark side of the outer hull includes this inward-facing vulnerability, where the boundary of space is weakened not by stars but by ordinary life. Windows are a special problem if they exist at all. Transparent materials are structurally and radiologically weaker than thick opaque shielding. They can darken under radiation, suffer impacts, and create thermal stress points. A generation ship may rely more on cameras and internal displays than large windows. Where optical access is necessary, protected ports, shutters, mirrors, or replaceable transparent layers reduce risk. Seeing outward has value. But maintaining pressure and shielding has greater value. The hull is also a social boundary. It defines where the human world ends. Beyond it lies no air, no pressure, no warmth, and no immediate help. Maintenance crews, engineers, and automated systems treat the hull as a living record of the voyage. Each scar marks contact with the interstellar medium. Each replacement panel records a decision about limited resources. Each inspection report becomes part of inherited responsibility. The dark side of the outer hull is that it must age while remaining essential. It cannot be allowed to fail, yet it cannot remain new. It is struck, chilled, irradiated, flexed, repaired, and watched. Its strength is not a fixed property from launch. It is a condition maintained by design, labour, knowledge, and material reserves. In the long crossing between stars, the hull becomes the ship's first memory of danger and its first answer to the emptiness outside. Heat and energy systems form the hidden climate of a generation ship. Outside the vessel, interstellar space remains cold and thin. Inside, Every living process depends on controlled energy flow, light for crops, warmth for bodies, movement of air and water, medical care, computing, manufacturing, and repair all require power. At the same time, every use of power produces waste heat. In deep space, heat cannot be carried away by wind or flowing water outside the hull. It must leave mainly as radiation from surfaces designed to glow in infrared light. The ship therefore lives between two limits. It must make enough energy to remain alive, and it must remove enough heat to avoid slowly cooking itself from within. Energy cannot be treated as a simple stored supply for a voyage lasting many generations. Chemical batteries and ordinary fuels hold limited energy for their mass. They may support local devices, emergency systems, or short-term operations, but they cannot by themselves maintain a large closed society across centuries. A generation ship requires a long-lived primary power source or a way to renew energy from carried materials. Known concepts include nuclear fission, nuclear fusion, and external beaming during part of a mission. Each has limits. Fission splits heavy atomic nuclei and releases energy. Fusion joins light nuclei and releases energy under extreme conditions. Both require fuel, control systems, shielding, heat engines, and long-term maintenance. Nuclear fission is the better established technology. On Earth, fission reactors have produced reliable power for decades in some settings. In spacecraft concepts, fission offers high energy density compared with chemical fuel. A generation ship using fission would require fissile material, control rods or other reactivity systems, coolant loops, turbines or direct conversion systems, radiation shielding, and long-term waste handling. Fissile material is fuel whose atomic nuclei can sustain a chain reaction. The dark side is not only the danger of an accident, it is the need to keep a complex reactor safe, controllable, inspected, repaired, and understood over centuries. Fusion offers more energy from certain fuels and produces different waste concerns, but sustained controlled fusion for power remains difficult. Research on Earth has made progress, yet practical, continuous, economical fusion power is still not a routine technology. A generation ship cannot depend on hopeful assumptions without proven engineering. If fusion is used in a realistic future design, it must include the full burden of confinement, heating, plasma control, neutron damage, fuel processing and replacement of worn parts. Plasma is gas so hot or energized that electrons are separated from atomic nuclei. Fusion systems may reduce some fuel mass problems, but they do not remove the need for radiators, shielding, and maintenance. Energy storage remains necessary even with a steady power source. Loads rise and fall. Agriculture may use cycles of light. Manufacturing may demand bursts of heat and electricity. Medical equipment, navigation, and emergency systems require backup power. Storage may involve batteries, flywheels, thermal reservoirs, chemical fuels, or other systems. A flywheel stores energy in a spinning mass. Each storage method has risks. Batteries age and can fail chemically. Flywheels require strong containment and bearings. Thermal storage needs insulation and temperature control. Chemical fuels can leak, react, or degrade. Long life requires not one storage system but many layers of backup. Waste heat becomes one of the most basic engineering facts of the vessel. Nearly all energy used inside eventually becomes heat. A lamp warms crops and walls. A computer warms its circuits and surrounding air. A motor warms bearings and coils. A human body turns food energy into heat. Even recycling systems and pumps add heat to the closed environment. This heat must be moved from where it is produced to where it can be rejected. On Earth, heat moves into air, water, soil, and sky. In interstellar space, the final step is radiation. The ship must shine heat away. Radiators are surfaces designed to emit heat into space. They may be panels, fins, loops, or large deployable structures. Their size depends on how much heat must be rejected and at what temperature they operate. Higher temperature radiators can reject more heat from a smaller area, but high temperatures stress materials and may be unsuitable for some systems. Lower temperature radiators need more area. Large radiators are vulnerable to dust, radiation, mechanical damage, and aging. They must face space while avoiding too much heat from other ship surfaces. They may need shutters, coatings, pumps, and repair mechanisms. Thermal control inside the ship requires circulation. Heat must be gathered from reactors, electronics, habitats, farms, and workshops. Coolants carry heat through pipes and heat exchangers. A coolant is a fluid used to move heat. Possible coolants include water, liquid metals, gases, or specialized fluids, depending on temperature and system needs. Pipes can leak, pumps can fail, heat exchangers can foul or corrode, valves can stick, sensors can drift. A thermal network aboard a generation ship is not a passive background feature. It is an active organ that must remain balanced. Too much heat harms life and machinery, but too little heat also creates danger. Some regions must stay warm enough to keep water liquid, air comfortable, and biological systems stable. Other regions must stay cold to preserve seeds, medicines, biological samples, or superconducting equipment if used. A superconducting material carries electric current with no resistance under certain conditions, usually at very low temperature. Maintaining cold areas in a warm ship requires refrigeration, which itself uses energy and produces more heat elsewhere. Cold is not free in a closed vessel. It is created by moving heat. The energy system affects social structure because power must be rationed during stress. If a reactor goes offline or radiators lose capacity, the ship may reduce lighting, manufacturing, entertainment, travel within the vessel, or comfort margins. Agriculture may receive priority because food production cannot stop for long. Life support must receive priority because air and water balance are immediate. Medical systems may compete with industrial repair. These choices are technical and social at the same time. A power shortage is not only a machine problem, it becomes a question of what the society preserves first. Fire is another energy hazard. Fire requires fuel, heat, and an oxidizer such as oxygen inside a spacecraft. Fire behaves differently from fire on Earth because airflow, pressure, and gravity may differ. Flames can produce toxic gases, consume oxygen, damage equipment, and spread through hidden spaces. A generation ship contains plastics, textiles, stored materials, plant matter, wiring, and machinery. Fire prevention depends on material choices, oxygen control, sensors, compartments, automatic suppression, and human training. Suppression systems must not poison the air or ruin critical equipment unless the alternative is worse. Energy generation also creates waste. Fission produces radioactive waste and activated materials. Fusion may produce neutron-damaged components and activated structures. Depending on fuel and design, chemical systems produce residues. Batteries contain reactive materials. A closed ship cannot simply discard dangerous waste without considering mass, trajectory, contamination, and future need for elements. Some waste must be shielded, some must be processed. Some may become a resource if materials are scarce. Waste handling becomes part of the energy economy. The dark side of heat and energy is that survival depends on continuous conversion. Nothing stays alive by being merely enclosed. Warmth, light, pressure, food, and information all require power flowing through machines. The ship must produce energy without poisoning itself, move heat without losing control, and radiate waste into a cold region that accepts heat only through light. Every comfort inside has a thermal cost. Every repair requires energy. Every safeguard adds mass and complexity. In the deep crossing, energy is not a stored treasure alone. It is a discipline maintained day after day, generation after generation, inside a vessel that must keep itself warm without burning, cool without freezing, and powered without end. Closed air and water cycles form the inner atmosphere of a generation ship. They begin with the simple fact that nothing essential can be allowed to disappear. Air cannot be opened to the outside. Water cannot be replaced from rivers, rain, or oceans. Every breath, every drop, every trace of vapor, and every dissolved chemical remains part of a controlled loop. The ship carries a small working portion of Earth's life-supporting chemistry, then depends on machines, plants, microbes, filters, and careful monitoring to keep that chemistry within narrow limits. Air is not only oxygen. A breathable atmosphere contains oxygen for metabolism, nitrogen or another buffer gas for pressure balance, carbon dioxide in small amounts, water vapor, and many trace gases. Oxygen supports the chemical reactions by which human cells release energy from food. Carbon dioxide is produced by those reactions and must be removed before it reaches harmful levels. Water vapor affect comfort, plant growth, condensation, corrosion, and microbial growth. Trace gases can come from plastics, paints, cleaning agents, electronics, crops, waste, and human bodies. In a closed vessel, even tiny emissions can build up if they are not removed. The air cycle must therefore separate, transform, and rebalance gases continuously. Carbon dioxide can be captured by chemical absorbents, solid filters, liquid systems, or biological processes. Plants and algae can use carbon dioxide during photosynthesis, the process by which light energy helps convert carbon dioxide and water into sugars and oxygen. Yet biological uptake changes with light, temperature, crop health, nutrient levels, and growth stage. Machines offer control and predictability, while living systems offer renewal and food production. A stable ship may use both, with neither trusted alone. Oxygen can be supplied in several ways. It may be released from stored tanks, generated by splitting water, or produced by photosynthetic organisms. Splitting water into hydrogen and oxygen requires energy and careful handling. Hydrogen is useful in some systems but can leak easily, and may create fire or explosion risks if mismanaged. Oxygen itself also increases fire risk when concentration rises too high. The ship must keep oxygen within a range that supports health without making materials easier to ignite. This range must be maintained across cabins, farms, workshops, medical rooms, and maintenance spaces. Nitrogen is quieter but still important. On Earth, nitrogen makes up most of the air and helps create normal pressure without too much oxygen. A ship can carry nitrogen or use another buffer gas, but losses through leaks, processing, or accidents must be controlled. Nitrogen is also part of proteins, DNA, and plant nutrients. The gas cycle connects with the food cycle and waste cycle because nitrogen moves between air, water, soil-like growth media, microbes, and bodies. Losing usable nitrogen into inaccessible forms can weaken agriculture and health. Water is equally central. It fills bodies, carries nutrients, moves heat, cleans surfaces, supports crops, and participates in chemical reactions. A person needs water for drinking and food preparation, but the larger system needs much more for hygiene, agriculture, cooling, processing, and storage. In a generation ship, water travels through many forms. It becomes drinking water, vapor in air, moisture in leaves, urine, wash water, coolant, ice, nutrient solution, and waste stream. The same molecules may pass through many people, machines, and plants over time. Water recovery begins with collection. Vapor can be condensed from air. Urine can be processed to recover water and useful chemicals. Wash water can be filtered and disinfected. Plant transpiration, the release of water vapor from leaves, can be captured by climate systems. Wastewater contains salts, organic matter, microbes, medicines, cleaning agents, skin cells, fibers, and trace metals. Treatment must remove what is harmful while preserving what is useful. Processes may include filtration, distillation, membranes, biological reactors, chemical oxidation, ultraviolet treatment, and mineral balancing. A membrane is a thin barrier that allows some molecules to pass while blocking others. Membranes can purify water, but they foul over time. Fouling means that materials build up on the membrane surface or inside its pores, reducing performance, filters clog, distillation equipment scales with mineral deposits. Biological reactors can shift if microbial communities change. Sensors can drift away from true readings in a closed water cycle. Treatment is not a single device, but a chain of processes watched by instruments and maintained by trained crews. Microbes are both helpers and hazards. Bacteria, fungi, and other microscopic life can break down waste, recycle nutrients, support plant roots, and help maintain ecological balance. They can also form biofilms inside pipes, contaminate water, release toxins, corrode materials, or cause disease. A biofilm is a thin living layer of microbes attached to a surface. In a spacecraft-like environment, biofilms can grow in hidden wet places, especially where flow is slow or nutrients collect. They may resist cleaning and become reservoirs of contamination. The ship cannot be sterile. Human beings carry microbial communities on skin, in the gut, and in the air around them. Plants and food systems also need microbial partners. The realistic goal is not total elimination of microbes, but control. Harmful organisms must be detected early. Useful communities must remain stable. Cleaning must avoid creating chemical residues that damage people, plants, or recycling systems. Antibiotic resistance and microbial adaptation remain concerns, especially in a closed population with limited medical supplies. Condensation is a quiet enemy. Water vapor in warm air can settle on colder surfaces as liquid droplets. These droplets can enter insulation, electrical systems, wall cavities, and seams. Moisture supports corrosion and microbial growth. Airflow and temperature control must prevent hidden wet zones. Surfaces must be shaped and drained so water returns to treatment systems rather than remaining trapped. A small patch of condensation can become a long-term maintenance problem if it hides behind panels. Chemical contamination also accumulates. Materials release volatile compounds, meaning substances that evaporate into air. Electronics may release small amounts of chemicals when heated. Cleaning fluids, medicines, personal care products, and manufacturing processes add further traces. Some compounds can irritate lungs or affect the nervous system. Others may harm crops or microbes needed for recycling. Monitoring must look beyond oxygen and carbon dioxide. It must track a changing mixture of trace substances that may interact in ways not fully predictable. Air and water cycles are linked through humidity, condensation, plant growth, waste treatment, and human metabolism. A failure in one loop can disturb the other. Too much humidity can damage equipment and encourage microbial growth. Too little humidity can dry mucous membranes, stress plants, and increase static electricity. Poor water treatment can release gases. Poor air treatment can affect water chemistry. The ship's life support is therefore not a set of separate machines. It is a connected system of loops, each influencing the others. The dark side of closed cycles lies in the absence of dilution. On Earth, pollution can disperse into a vast atmosphere or flow into large bodies of water, although that does not make it harmless. Inside a generation ship, there is no vast outside reservoir. Every contaminant remains nearby until removed, transformed, stored, or absorbed. Every leak is a loss from a limited inventory. Every imbalance returns through the loop. The air and water that sustain life also carry the record of every process aboard, making cleanliness, chemistry, biology, and repair part of one continuous discipline. Food production systems sit deeper inside the generation ship, where light is artificial, seasons are designed, and soil is not a natural landscape but a managed support for life. Food cannot be treated as cargo alone. Stored food can help during early travel, emergencies, or crop failure, but it cannot feed a society indefinitely unless the storage mass is immense and perfectly preserved. A generation ship must grow much of its food again and again, using the same atoms of carbon, nitrogen, phosphorus, potassium, calcium, iron, and many other elements as they cycle through bodies, waste, water, and plants. The farm inside the ship is not a field under a sky. It is a controlled environment where temperature, humidity, airflow, light, nutrients, pests, microbes, and harvest timing are regulated. Plants need light for photosynthesis, carbon dioxide from air, water, mineral nutrients, and suitable temperatures. They also need space for roots and leaves. Every square meter used for crops must be lit, cooled, cleaned, and maintained. Food production therefore becomes one of the largest demands on the ship's energy and life support systems. Artificial lighting is central. Sunlight does not reach the ship with useful strength in interstellar space, so crops depend on lamps. Plants use mainly certain wavelengths of visible light, especially red and blue light, though other wavelengths can affect growth and development. Efficient lamps can provide selected light, but not all light becomes plant matter. Much becomes heat. The more food the ship grows, the more heat must be removed. A farm is therefore also a thermal machine, converting electricity into light, biomass, water vapor, oxygen, and waste heat. Crop choice shapes the whole system. Grains provide carbohydrates and calories, but they may require space and processing. Legumes can provide protein and help with nitrogen cycling when paired with suitable microbes. Leafy greens grow quickly and provide vitamins, but they are not dense sources of energy. Tubers and root crops can produce many calories in compact areas. Fruits add nutrients and variety, but may require more time, structure, and pollination. Algae and other microorganisms can grow efficiently in tanks, offering protein, fats, and oxygen production. But they may not satisfy cultural expectations for food without processing. A complete diet needs more than calories. It needs essential amino acids, fats, vitamins, minerals, fiber, and safe water. Essential amino acids are protein building blocks that the human body cannot make in sufficient amounts. Some vitamins degrade during storage and processing. Others depend on fresh production or microbial synthesis. Deficiencies may appear slowly through weakened immunity, poor growth, bone loss, anemia, nerve damage, or reproductive problems. The farm must therefore be planned as a nutritional system, not just a source of harvest weight. Nutrient cycling is difficult because elements move through many forms. Human waste, plant residues, uneaten food, and microbial biomass contain valuable nutrients. These materials can be processed into fertilizers, but they also contain pathogens, medicines, salts, heavy metals, and chemical residues. Composting, anaerobic digestion, mineral recovery, and other processes can return nutrients to crops. Anaerobic digestion is microbial breakdown without oxygen, producing gases and nutrient-rich residues. Each method requires control to avoid contamination and loss. Phosphorus is a quiet concern. It is essential for DNA, cell membranes, bones, and energy transfer in cells. On Earth, agriculture depends heavily on mined phosphate rock. A generation ship must carry its phosphorus and keep it in circulation. Losses into inaccessible deposits, filters, sludge, or discarded materials reduce long-term fertility. Nitrogen, potassium, sulfur, magnesium, and trace elements require similar attention. A closed farm must account for grams of nutrients over generations. Because small losses repeated often become large losses. Growth methods may include hydroponics, aeroponics, controlled soil-like media, algae bioreactors, and fungal cultivation. Hydroponics grows plants with roots in nutrient solution or inert support. Aeroponics grows roots in air with nutrient mist. These methods allow precise control and reduce mass compared with deep soil, but they depend heavily on pumps, sensors, sterilization, and stable chemistry. Soil-like media can buffer changes and support diverse microbes, but they are heavier and harder to monitor. No method is free of risk. A resilient ship may combine several methods so one failure does not remove all food. Pollination must be managed. Some crops self-pollinate. Others need movement of pollen by wind, vibration, insects, or human tools. Insects can serve useful roles, but they also introduce ecological complexity. Bees, flies, beetles, or other pollinators require habitat, food, disease control, and containment. Mechanical pollination can replace insects for some crops, though it adds labor and equipment. Crop reproduction must be reliable because seeds are not only food but also the future of the farm. Seed banks preserve genetic diversity. Seeds can remain viable for different lengths of time depending on species and storage conditions. Low temperature and low moisture help many seeds last longer, but viability declines eventually. The ship must grow replacement seed, test germination, prevent disease, and maintain diverse lines. Genetic diversity helps crops adapt to changing conditions and resist disease. A narrow crop base may be efficient at first but fragile over time. Mutations from radiation, copying errors, and selection pressures inside the farm may alter plant populations across generations. Plant disease can spread quickly in a closed farm. Fungi, bacteria, viruses, and pests may move through air, water, tools, clothing, or nutrient systems. A pathogen that would affect one field on Earth can threaten a large fraction of food production if crops are genetically similar and grown under uniform conditions. Prevention depends on quarantine, sanitation, resistant varieties, environmental control, and early detection. Treatments must be chosen carefully because pesticides and disinfectants can remain in closed loops and affect people, microbes, and water systems. Food animals create another layer of cost. Large animals require feed, space, water, veterinary care, waste handling, and long generation times. They convert plant matter into meat, milk, or eggs with losses of energy and nutrients. Small animals, fish, or insects may be more efficient, but they still need controlled habitats and disease management. A generation ship may rely mostly on plants, fungi, algae, and microbial protein because these can use space and nutrients more efficiently. Cultural preference may persist, but physics and ecology push toward efficiency. Food is also social memory. Meals carry identity, comfort, ceremony, and continuity. Yet the farm cannot supply unlimited variety. Ingredients may be repeated. Flavors may depend on preserved cultures, herbs, fermentation, and careful processing. Fermentation uses microbes to transform food, improving preservation, digestibility, or flavor. It also requires safety, because useful microbes and harmful contamination can look similar until tested. The emotional value of food cannot be separated from its biological role, but the farm's limits remain firm. The dark side of shipboard food is ecological fragility in a small volume. A farm that appears green and abundant is still an artificial ecosystem held within mechanical boundaries. It depends on lamps, pumps, sensors, clean water, balanced nutrients, healthy microbes, and stored knowledge. A bad harvest is not a market problem. It is a survival problem. There is no neighbouring valley, no ocean fishery, no outside grain reserve. The food system must produce nourishment, preserve diversity, recycle waste, resist disease, and remain acceptable to the people who live from it. Inside the ship, agriculture becomes a carefully lit island of life, productive because it is watched, and vulnerable because it has nowhere else to spread. Artificial gravity and motion shape the body's experience of the generation ship. In open space, a vessel moving steadily does not create weight by speed alone. Once the engines stop pushing, everything inside follows the same path, and bodies float unless another force acts on them. Human beings evolved under Earth's gravity, where bones, muscles, blood flow, balance, and development all respond to a constant downward pull. A generation ship must either accept the harms of a long weightlessness or create a substitute. The most practical known method is rotation. Rotation can create artificial gravity through centripetal acceleration. Centripetal acceleration is the inward acceleration needed to keep an object moving in a circle. Inside a rotating habitat, the floor pushes inward on a person's feet, and the body feels that push as weight. The effect is often described as outward because the person feels pressed toward the floor, but the physical force from the floor points toward the center of rotation. The result can imitate some effects of gravity without needing a planet. The size of the rotating section matters. A small rotating room must spin quickly to create Earth-like weight. Fast rotation can disturb the inner ear and make movement uncomfortable. The inner ear senses rotation and balance. When a person turns the head inside a rotating habitat, the apparent direction and strength of forces can shift, producing dizziness, nausea, or disorientation. A larger radius allows slower rotation for the same artificial gravity, reducing these effects. This pushes designs toward broad rings, long arms, or large rotating cylinders. A rotating habitat is not a simple wheel added to a ship. It must carry air, water, power, data, people, crops, machinery, and structural loads. If the rotating section connects to non-rotating parts, bearings or magnetic couplings may be needed. A bearing allows one structure to move relative to another while carrying loads. Large bearings operating for centuries are difficult machines. They must handle wear, lubrication, dust, vibration, thermal changes, and repair. Magnetic systems can reduce contact but require control, power, and backup. This structure also faces stress from rotation. Every part of the spinning habitat tends to move in a straight line, while the structure keeps it in circular motion. This creates tension through the ring or cylinder. Strong materials can handle such loads, but strength must be balanced against mass. The larger the habitat and the greater the artificial gravity, the greater the structural demands. Cracks, fatigue, and imbalance can threaten both comfort and safety. A rotating system must be monitored for tiny changes in shape and vibration. Balance is essential. If mass shifts unevenly inside the rotating habitat, the spin can wobble. People moving, water tanks filling, crops growing, waste being processed, and cargo being relocated all alter mass distribution. On Earth, buildings rest on ground that absorbs small imbalances. In space, a rotating habitat carries its own motion. Control systems may move counterweights, pump fluids, adjust spin, or use gyroscopes to stabilize orientation. A gyroscope is a spinning device that helps measure or maintain direction. These systems must respond quietly and continuously. Artificial gravity need not equal Earth gravity. Lower levels may reduce structural demands and energy costs, but biological effects remain uncertain. Human experience in low gravity comes mainly from astronauts in weightlessness, and from brief stays on the Moon. The Moon's gravity is about 1/6 of Earth's. Mars has about 1/3 of Earth's gravity. No human population has grown from conception to old age under partial gravity. It remains uncertain what minimum gravity is needed for normal pregnancy, childhood bone growth, muscle development, immune function, balance, and long-term health. Weightlessness has well-known effects. Astronauts in orbit lose bone, mineral, and muscle mass without exercise. Fluids shift toward the head. The heart and blood vessels adapt. Balance changes. Vision problems have been observed in some astronauts during long missions. Exercise, diet, and medical monitoring help, but they do not fully replace gravity. A generation ship cannot treat these effects as temporary because its people may live entire lives aboard. Artificial gravity is therefore not only a comfort, it may be a biological requirement. Rotation also affects everyday motion. Dropped objects do not fall exactly as they do on Earth. They may appear to curve because of the Coriolis effect, an apparent deflection seen in rotating systems. A person walking inward or outward from the spin axis may feel unusual sideways forces. Water surfaces, smoke, dust, and air currents behave differently from their behavior under natural gravity. In a large, slowly rotating habitat, these differences may be small enough for daily life. In a smaller or faster one, they may become constant reminders that weight is being made by motion. The ship may contain regions with different gravity levels. The main living areas may rotate. Central hubs near the spin axis may have very low gravity. Maintenance shafts, docking spaces, storage areas, and industrial sections may be weightless or weakly weighted. Moving between these regions requires training and safety systems. Tools, fluids, and bodies behave differently depending on location. A worker accustomed to the floor of the habitat may need restraints and handholds in central areas. A child raised in rotating gravity may find weightless spaces disorienting. Air and water circulation must be designed for the rotating frame. Warm air rises only if there is an effective direction of weight. In low or changing gravity, fans become essential for mixing air and preventing carbon dioxide from gathering near faces. Water does not drain normally without gravity. In rotating areas, water can flow toward the outer floor, but pumps and separators still matter. Toilets, showers, kitchens, farms, and medical systems all depend on predictable fluid behavior. Artificial gravity helps, but it does not make the ship identical to Earth. Spin changes the meaning of architecture. Floors curve gently in a ring or cylinder. The horizon may bend upward in the distance. Tall structures point toward the spin axis. Elevators moving inward reduce apparent weight. Moving outward increases it. The highest buildings, if any exist, reach toward weaker gravity. The safest sleeping and medical areas may be placed where forces are steady and vibration is low. The design of rooms, corridors, and farms follows the geometry of rotation. The dark side of artificial gravity is that it solves one problem by creating many others. Without it, human bodies may weaken and develop in uncertain ways. With it, the ship must carry rotating mass, bearings, structural tension, vibration control, and complex transitions between moving and non-moving sections. It must protect people not only from space outside, but from the mechanical conditions that make life inside possible. Weight becomes an engineered service, maintained by spin, structure, measurement and repair. In the inner regions of the vessel, the simple feeling of standing on a floor depends on a whole machine turning steadily in the dark. Population and genetics lie deeper inside the generation ship, within the bodies and family lines of the people who keep the vessel alive. A generation ship is not only a machine carrying passengers, it is a moving population whose future depends on birth, death, health, heredity, and social care. The voyage lasts long enough for many people to be born, grow old, and die without leaving the ship. This makes biology part of navigation. The vessel must preserve not only air, water, and food, but also the human capacity to continue as a healthy community. A population that begins too small faces risks that do not appear immediately. One risk is inbreeding, which means reproduction among closely related people, often enough that harmful inherited traits become more likely to appear. Every person carries some genetic variants that can contribute to disease if paired with a similar variant from another parent. In a large population, such pairings are less likely for rare variants. In a small, isolated population, relatives share more ancestry, and the chance of pairing harmful variants rises over generations. Another risk is genetic drift. Genetic drift is random change in the frequency of genetic variants across generations. It is strongest in small populations. A trait can become more common or disappear, not because it helps or harms survival, but because of chance. In an isolated ship, random losses matter because there is no outside population to restore missing diversity. Genetic diversity is not valuable only as a symbol. It helps a population respond to disease, reproductive challenges, and changing conditions. Low diversity can make a community more fragile. The exact minimum safe population for a multi-generational interstellar voyage remains uncertain. Studies use models with different assumptions about trip length, family structure, reproductive patterns, medical care, stored embryos, and genetic screening. Results vary widely because the problem depends on many details. A ship carrying only a few families would face severe long-term risks. A ship carrying thousands or more would have a stronger biological foundation, but would need much more mass, food, living space, power, and governance. Biology and engineering pull against each other. Stored genetic material may reduce some risks. Frozen embryos, sperm, eggs, and cell lines can preserve diversity beyond the living population. Cryopreservation is storage at very low temperature to slow biological change. It is already used in medicine and research, but maintaining viable samples across centuries would require stable cold storage, protection from radiation, careful records, and working reproductive medicine. Stored material is not a simple solution. It depends on machines, skilled personnel, consent rules, cultural acceptance, and the continued ability to use it safely. Genetic screening may help identify inherited disease risks, but it also creates ethical and practical burdens. Screening can detect some known variants linked with disease. It cannot predict every health outcome, because many traits involve many genes and environmental factors. A narrow focus on avoiding disease can also reduce diversity if applied too strongly. The ship must balance health protection with respect for persons, family life, and genetic variation. Scientific knowledge can guide decisions, but it cannot remove the moral weight of reproductive policy in a closed population. Disease spreads differently in an isolated community. Some infectious diseases might disappear if no outside source brings them in, and if infected people recover or die. Other microbes live quietly in human bodies and can reappear when immunity changes. Viruses can persist in latent form. Bacteria can evolve resistance. Fungi can occupy damp places. The ship's population has no new immigrants bringing common Earth infections, but it also has limited exposure to the wider microbial world. Immune systems develop through contact with microbes. A highly controlled environment may alter immune training in ways that are not fully understood. Medical genetics becomes part of daily health care. Doctors must track family histories, inherited conditions, fertility patterns, pregnancy outcomes, childhood development, and adult disease. Records must be accurate across generations. Errors in ancestry records can affect reproductive planning. Loss of medical archives can hide risks. Privacy remains important, but privacy exists within a small community where information can be life-saving. The ship must maintain trust so people continue to share medical information without fear of misuse. Reproduction cannot be treated as only private if the population is small and isolated. Birth rates affect food demand, housing, education, labor, medical care, and long-term survival. Too few births can leave the ship without enough trained adults. Too many births can strain life support and resources. Uneven birth timing can create age gaps that weaken knowledge transfer. A stable population requires planning, but planning can become coercive if handled without rights and consent. The dark side of population management lies in this tension between individual freedom and collective survival. Age structure matters as much as total number. A ship full of older adults cannot sustain labor and reproduction for long. A ship with too many children may overburden caregivers and education systems. A balanced population includes infants, children, adults, elders, specialists, apprentices, and people unable to work because of illness or disability. Each group has needs and roles. Elders may carry memory and judgment. Adults maintain systems. Children represent continuity but require long investment before they can contribute fully. Fertility may be affected by radiation, stress, nutrition, illness, contaminants, gravity level, and social conditions. Human reproduction is sensitive to body health and environment. Pregnancy aboard a ship requires stable gravity or a proven alternative, clean air, safe water, adequate nutrients, infection control, emergency medicine, and neonatal care. A small rise in pregnancy complications can have large consequences over generations. Observations from Earth medicine and spaceflight provide partial guidance, but no human community is reproduced for centuries in a closed spacecraft environment. Mutation is another slow force. Mutations are changes in genetic material. They occur naturally during cell division and can also be caused by radiation and chemicals. Most have little effect, some are harmful, and a few may be beneficial in certain environments. Increased radiation exposure could raise mutation rates in reproductive cells if shielding is insufficient. Medical monitoring can detect some effects, but not all. Over generations. The genetic health of the population depends on shielding, screening, treatment, and reproductive outcomes. The ship also contains non-human genetics, crops, microbes, fungi, and possible animals carry their own hereditary material. Their diversity affects food security, waste recycling, disease control, and medicine. Human genetics cannot be separated completely from this wider biological library. A crop blight, a microbial shift, or loss of stored seed diversity can affect human survival as directly as a medical disorder. The ship's living inventory is a shared genetic reservoir, maintained through storage, breeding, testing, and renewal. The dark side of population and genetics is that the future becomes measurable but not fully controllable. A generation ship cannot rely on chance alone, yet it cannot turn human life into a simple breeding plan without damaging the society it hopes to preserve. It must carry enough people, enough diversity, enough medical knowledge, and enough humility before uncertainty. Within the hull, heredity moves quietly from parent to child, from archive to clinic, from choice to consequence. The voyage continues not only through space, but through the fragile inheritance of living bodies. Social order and culture form the inner framework that holds the population together. A generation ship cannot survive by machinery alone, because every machine depends on people who learn, maintain, interpret, and decide. The vessel is a closed society with limited space, limited resources, and no outside authority close enough to intervene. It carries laws, customs, education, labor systems, rituals, archives, and shared meanings. These are not decorative additions to the mission. They are part of the life support structure, because disorder can damage air, water, food, power, and trust as surely as a failed valve or cracked seal. Governance begins with the problem of legitimacy. The first crew may accept the mission because they chose it or were selected for it. Later generations inherit the consequences of that choice. Authority must explain why decisions made before their birth still shape their lives. A command system may work during short emergencies, but a society lasting centuries needs institutions that people regard as fair enough to obey. These institutions may include councils, courts, technical boards, elected roles, inherited offices, or hybrid systems. The exact form can vary, but it must handle conflict without breaking the ship. Law aboard the vessel is shaped by physical limits. On Earth, communities can sometimes separate, migrate, import supplies, or appeal to higher authorities. On a generation ship, separation is difficult, supplies are finite, and every conflict occurs within shared walls. A crime against a person is also a threat to community stability. Damage to equipment may endanger everyone. Imprisonment uses space, food, air, and labor. Exile is impossible in the ordinary sense. Justice must protect individuals while preserving the functioning of the whole society. This creates pressure toward prevention, mediation, restitution, and careful mental health care, but serious harm still requires firm response. Labour cannot be optional in the same way it may appear in wealthy open societies. Air processing, agriculture, medical care, education, hull inspection, waste recycling, software maintenance, and power systems require continuous work. Some tasks are routine and repetitive, others require rare expertise. The ship must decide how labour is assigned, rewarded, taught, and shared. If too many people reject essential roles, systems decline. If labour is imposed too harshly, resentment grows. A stable order must make necessary work meaningful enough, fair enough, and visible enough to continue across generations. Education becomes one of the central institutions. Children must learn ordinary language, mathematics, biology, history, engineering, medicine, ecology, and the practical habits of living in a closed vessel. They do not need every person to become a specialist. But the society must always produce enough specialists to replace those who age or die. Knowledge cannot remain in machines alone. Archives can be corrupted, interfaces can become obsolete, and procedures can be misunderstood. Living teachers interpret knowledge, correct errors, and connect technical facts to judgment. The curriculum must preserve accuracy without freezing thought. If education becomes too narrow, the society may lose the ability to respond to unexpected failures. If it becomes too loose, critical skills may vanish. The ship needs people who can maintain established systems, and people who can question them safely. Scientific method remains important because many problems aboard the vessel require observation, testing, and correction. Tradition may help preserve useful practices, but tradition without verification can carry mistakes forward. Archives serve as cultural memory. They may contain engineering drawings, medical records, star maps, literature, music, languages, law, biographies, scientific databases, and records of Earth. Yet storage is not the same as remembrance. Data must be readable, indexed, translated if language changes, and protected from damage. People must know why records matter. A library ignored for generations becomes fragile even if the files remain intact. Cultural continuity requires repeated use. Language may change inside the ship. Isolated communities on Earth show that pronunciation, vocabulary, and grammar can shift over time. A generation ship has schools and archives that may slow change, but everyday speech still adapts. Technical language may remain more stable because safety depends on precision. Informal language may change faster. Over centuries, the ship's speech could differ from the language of its founders. This is not failure by itself, but it creates a need for translation across old records and current understanding. Culture also regulates behavior where law cannot reach every moment. Shared meals, ceremonies, naming practices, art, games, mourning customs, and maintenance rituals help people feel that life is more than survival. These practices can strengthen trust and patience. They can also exclude, pressure, or divide. In a small society, cultural conflict has fewer places to disperse. Differences in belief, status, family line, occupation, or habitat region may harden if not addressed. The vessel must allow variation without allowing social fracture to threaten essential systems. Status is a serious risk. Some roles control power, air, water, food, records, or security. If these roles become permanently attached to certain families or groups, inequality can deepen. Technical expertise may turn into political power because others cannot easily challenge specialists. At the same time, ignoring expertise can be dangerous. A reactor engineer and an untrained citizen do not hold equal knowledge about reactor safety. The society must respect competence without allowing competence to become unchecked rule. Conflict is inevitable. People disagree over resources, relationships, work, reproduction, education, religion, memory, and risk. A closed society cannot depend on distance to cool every dispute. It needs habits of negotiation, transparent evidence, accountable leadership, and safe channels for complaint. Hidden grievances can become sabotage, withdrawal, factionalism, or despair. Surveillance may seem attractive in a fragile environment, but constant surveillance can damage trust and dignity. The balance between safety and freedom becomes one of the deepest social problems aboard the vessel. Information control carries similar danger. Leaders may be tempted to hide risks to prevent panic. Engineers may simplify reports to avoid public confusion. Families may conceal illness or rule violations. Yet a society that cannot see its real condition cannot make sound choices. Panic is harmful, but false reassurance is also harmful. Reliable public knowledge becomes part of survival. The population needs ways to understand danger without being overwhelmed by it. The ship also contains memory of Earth, but that memory changes with distance and time. For the first generation, Earth is lived experience. For later generations, it is archive, story, image, and inherited identity. Some may treat Earth as a sacred origin. Others may see it as irrelevant or as the source of confinement. Cultural order must hold these different meanings without requiring one emotional response from everyone. The society's relationship to Earth may influence law, education, art, and the value placed on the mission itself. The dark side of social order is that survival can become a reason to control too much. Every authority can claim necessity. Every restriction can be described as protection. Yet a society that strips away consent, privacy, learning, and cultural life may preserve bodies while harming the human purpose of the voyage. The ship must remain orderly enough to keep systems alive and open enough to let persons live as more than components. Inside the hull, culture becomes a quiet engine, carrying rules, memory, work, meaning, and conflict through the long passage. The human mind indoors becomes one of the deepest regions of the generation ship. It exists behind the hull, behind the farms, behind the laws, and behind the inherited routines of the community. The vessel contains bodies, but it also contains attention, memory, fear, hope, boredom, grief, anger, and belonging. A closed environment shapes these states continuously. The walls do not need to press inward for confinement to be real. The mind notices limits through repeated corridors, repeated faces, repeated work, and the knowledge that no open landscape lies beyond any door. Human psychology evolved in changing environments filled with weather, daylight, seasons, varied terrain, and wide social networks. A generation ship replaces these conditions with artificial cycles, controlled air, designed lighting, limited movement, and a small society. This does not mean that mental health must collapse. Human beings can adapt to submarines, polar stations, space missions, ships, monasteries, prisons, and crowded cities. Yet adaptation has costs, and those costs increase when departure is impossible and duration extends beyond a lifetime. Confinement affects perception of choice. A person may have work, family, education, recreation, and private space, but the larger boundary remains fixed. There is no countryside to leave for, No other city to enter, no natural horizon to approach. Even if the vessel is large, its size is finite and known. The mind can learn every route, every public room, every view, every sound of machinery. Familiarity can become comfort, but it can also become pressure. The same environment that supports stability can reduce the feeling of possibility. Monotony is not merely a lack of entertainment, it can alter attention, motivation, and time sense. Repetition may make days blur together. Artificial schedules can provide structure, but structure without novelty can feel heavy. Work rotations, education, art, exercise, ceremonies, and changing social roles can help create variation. Still, variation inside a closed system is partly manufactured. The mind may recognize this and feel the difference between designed novelty and the uncontrolled richness of a planet. Light strongly influences mood and physiology. Human sleep and waking patterns are tied to circadian rhythms, internal cycles shaped by light, darkness, activity, and hormones. Circadian means roughly daily. On a generation ship, there is no natural sunrise through an atmosphere and no true night sky above a landscape. Lighting systems must create day and night patterns that support sleep, alertness, farming, and social life. Poorly timed light can disturb sleep, increase fatigue, reduce concentration, and affect mood. Good lighting helps, but it remains a constructed substitute for planetary cycles. Privacy becomes a scarce mental resource. Even in a large vessel, people live within a known population, reputation travels, family histories remain visible, work performance, illness, conflict, and personal choices may be difficult to hide. Some degree of privacy is necessary for dignity and emotional recovery. Private rooms, protected communication, confidential medical care, and social norms of non-intrusion help preserve the self. Without them, people may begin to feel observed even when no one is watching. Crowding does not depend only on the number of people per room, it also depends on control over contact. A person who can choose solitude may tolerate density better than one who cannot. A generation ship must provide spaces for gathering and spaces for withdrawal. It must protect quiet as carefully as it protects air. Noise from machinery, ventilation, pumps, footsteps, alarms, and shared activity can become a constant strain if not controlled. In a vessel where sound travels through structure, silence may be engineered rather than natural. Mental health care must be continuous and ordinary, not only emergency response. Depression, anxiety, trauma, psychosis, addiction, obsessive behavior, family violence, and grief can occur in any society. A closed ship adds stresses that may increase risk. Treatment may include counseling, medication, social support, meaningful work, rest, exercise, conflict resolution, and environmental changes. Medication supplies must be produced, stored, or substituted over time. Therapists and physicians must be trained each generation. Stigma can prevent care, especially in a small community where people fear being judged or losing roles. Grief has a special form aboard the ship. People die in the same closed world where they were born. Their bodies must be handled through burial alternatives compatible with life support, such as cremation, chemical processing, or nutrient recovery, depending on culture and safety. Mourning takes place without the vastness of Earth's landscapes, cemeteries, or ancestral towns. Memory may attach to rooms, archives, names, and shared rituals. Grief can strengthen continuity. but accumulated loss across generations can also deepen the feeling of enclosure. Identity may become divided between personal life and mission life. Some people may feel pride in maintaining the voyage, others may feel trapped by a purpose chosen long before them. Both responses can exist in the same society. A person can value the community and still resent its limits. The mind does not always follow official meaning. If the mission becomes the only accepted source of identity, those who doubt it may be treated as threats. If the mission loses all meaning, maintenance and sacrifice may weaken. Psychological health requires room for loyalty, doubt, and ordinary private desire. The absence of direct nature matters. Plants in farms, water reservoirs, soil-like growth media, and simulated landscapes can help, but they are not the same as forests, rivers, deserts, storms, or open oceans. Research on Earth suggests that contact with natural environments can support well-being, though the exact mechanisms vary. A generation ship can provide gardens, varied light, textured spaces, and living ecosystems. These may reduce stress and support attention. Yet they are enclosed nature, curated and dependent on machinery. Their fragility may be visible to everyone. Children learn the ship as normal. Their mental maps begin with corridors, rotating floors, artificial skies, and stories of planets. They may not feel the same loss as the first generation, because they have no direct memory of open air. Yet they may face another pressure, the awareness that the world available to them was chosen before they existed. Education can present the vessel as home, mission, ecosystem, and inheritance. It cannot remove the fact that other forms of life are known through records rather than experience. Fear also changes shape. Immediate fear may come from alarms, illness, accidents, or conflict. Deeper fear comes from dependence. Every person depends on systems they cannot fully understand. The air continues because unseen machines work. Food grows because many processes remain balanced. The hull holds because inspections are accurate. Trust in the ship is therefore partly trust in strangers, ancestors, and descendants. When trust weakens, ordinary sounds can become signs of danger. When trust holds, the same sounds become the background of safety. The dark side of the human mind indoors is not only madness or panic, it is the slow narrowing that can occur when life has too few exits, too few surprises, and too many inherited necessities. A generation ship must protect imagination as well as oxygen. It must make space for rest, solitude, beauty, disagreement, play, mourning, and care. The mind inside the vessel is not separate from engineering. It is affected by light, noise, space, schedule, privacy, work, culture, and truth. In the innermost human region, survival depends on keeping consciousness from becoming another closed loop with no renewal. Children of the voyage live at the innermost edge of the generation ship's purpose. They are not cargo, crew in the original sense, or planners of the journey. They are people born inside a moving world already shaped by decisions made before their lives began. Their first air is recycled air. Their first water has passed through many systems before reaching them. Their first ground may be the curved floor of a rotating habitat. Their first sky may be a ceiling of controlled light, a display, or a protected view of stars. For them, the ship is not a temporary vessel, it is the only known home. Birth aboard the ship carries biological, medical, and social weight. Pregnancy requires stable nutrition, controlled radiation exposure, careful medical monitoring, and a safe gravity environment or a well-understood substitute. The developing body depends on signals from the environment. Bones, muscles, balance systems, blood flow, and immune function all develop through interaction with gravity, motion, microbes, food, and care. On Earth, these conditions vary widely but remain anchored by a planet. On the ship, they are designed and maintained. If those designs are flawed, children may reveal the flaw through growth itself. The first years of life require protection from hazards that adults can understand but infants cannot. Air quality, surface cleanliness, water purity, noise, lighting, infection control, and emotional caregiving all matter. A baby depends entirely on others and on the stability of the surrounding systems. A power failure, crop disease, medical shortage, or social conflict reaches children through adults before children can name the danger. This makes childcare a shared survival function, not only a private family responsibility. Childhood development inside the vessel depends on movement. Children learn by crawling, standing, falling, reaching, climbing, and exploring. Artificial gravity, if present, gives a direction for weight, but it may not perfectly match Earth. Rotating environments can create unusual motion effects. Low gravity areas may be exciting but risky for developing bodies. The ship must provide safe spaces where children can test strength, balance, and coordination without damaging themselves or equipment. Play becomes part of physical adaptation. It is also part of learning the rules of a closed world. Education begins early because the ship is complex. Children learn ordinary skills such as language, counting, sharing, hygiene, and care for living things. They also learn that air vents must not be blocked, water must not be wasted, tools must return to assigned places, and alarms must be understood. On Earth, a child can break many rules without threatening a habitat. On the ship, some mistakes carry wider consequences. Education must therefore teach caution without creating constant fear. A child raised only in warning may become anxious. A child raised without warning may become dangerous. The moral burden placed on children is quiet but heavy. They inherit a mission they did not choose. Adults may teach that the voyage protects humanity, serves knowledge, reaches a new world, or fulfills duty to ancestors. These meanings may be sincere and useful, yet the child still grows into a life with limited exits. Consent cannot be fully given before birth. This fact does not make the child's life empty or invalid, but it makes the ethics of the voyage difficult. A society aboard the ship must recognize the child as a person, not merely as a link in a planned chain. Rights for children must be more than promises. They need care, safety, education, privacy, room for play, protection from exploitation, and a voice appropriate to their maturity. They also need freedom to imagine lives that do not exactly match adult plans. A closed ship may be tempted to direct children early into needed professions. Engineers, doctors, farmers, teachers, and technicians must be replaced. Talent cannot be ignored. Still, turning childhood into workforce preparation alone narrows the person. The ship survives through skills, but it remains worth preserving only if children can become full human beings. Adolescence may be especially difficult. The young person begins to understand the scale of the vessel, the limits of choice, the history of the mission, and the authority of adults. The body changes, social bonds deepen, and identity becomes more independent. In an open world, adolescence often includes testing boundaries by distance, travel, new groups, and risk. On the ship, distance is limited and risk can endanger others. The society must provide safe forms of independence, challenge, and disagreement. Without them, rebellion may turn towards systems, relationships, or the self. Generational difference grows naturally. The first generation remembers Earth. The next generation remembers people who remembered Earth. Later children inherit images, recordings, lessons, and rituals rather than living witnesses. The emotional meaning of the voyage changes with each step away from origin. For children born later, Earth may be no more immediate than ancient history. The ship's corridors, farms, schools, clinics, and quiet machines may feel more real than oceans or continents. This shift is not ignorance. It is the normal result of experience. The destination may also change meaning. Children may be taught about a target star, possible planets, and the reasons for the journey. Yet a destination that lies beyond their expected lifetime can feel abstract. Some children may live and die before arrival. Others may belong to the generation that approaches the system. These differences can shape identity. Those far from arrival may value maintenance and continuity. Those near arrival may face uncertainty, fear, and pressure. Each generation carry a different portion of the voyage. Health records follow children from birth. Growth curves, radiation exposure, genetic information, infections, nutrition, injuries, learning needs, and mental health all become part of medical history. These records help protect the individual and the population. They also create privacy concerns. In a small society, sensitive information can shape education, work assignments, reproductive expectations, and social standing. Children grow under records they did not choose to create. The ship must protect them from being reduced to data while still using data to care for them. Family structure may adapt to the closed environment. Biological parents may raise children, but broader caregiving networks may be necessary because essential labor cannot stop. Communal childcare, apprenticeships, elder involvement, and professional education may all blend. This can give children many trusted adults. It can also blur responsibility if no one is clearly accountable. Stability, affection, and reliable attachment remain important. A child needs more than efficient management. A child needs known care. The children also carry culture forward. Songs, stories, names, recipes, ceremonies, jokes, technical habits, and moral assumptions survive only if children receive and transform them. They do not copy the past exactly, they adapt it to the ship they know. A ritual from Earth may shift in meaning when performed under artificial light. A story about rain may become a lesson about water cycles rather than a memory of weather. Culture remains alive by changing. But too much loss can weaken continuity. The balance is delicate. The dark side of children aboard a generation ship is the joining of innocence with necessity. Each child is loved as an individual and also needed by the future. Each grows in safety only because many limits are imposed. Each receives a home that is also a machine, a society that is also a mission, and a history that is also an obligation. The ship must not hide this truth, but it must not place its full weight on young shoulders too early, in the deepest human layer of the voyage. Continuity depends on children who are allowed to belong, to question, to learn, and to become more than proof that the journey continues. Arrival and planetary reality form the innermost boundary of the generation ship's journey, where distance no longer hides the destination inside a point of light. A star system reached after centuries is not automatically a home. It is a physical environment with its own radiation, gravity, planets, small bodies, dust, magnetic fields, and chemical limits. The ship may arrive near a star that was chosen because observations from far away suggested promise. Those observations can reveal size, Orbit, mass, temperature estimates, and parts of an atmosphere for some planets. They cannot guarantee safety, habitability, or welcome. A planet in the habitable zone is not necessarily habitable. The habitable zone is the range of distances from a star where liquid water could exist on a planet's surface under suitable atmospheric conditions. This definition is useful but incomplete. A planet may orbit in this zone and still have no water, too much atmosphere, too little atmosphere, poisonous chemistry, intense radiation, unstable climate, or no solid surface. It may be tidally locked. With one side facing the star for long periods, it may suffer strong flares if the star is active. It may have a gravity that strains human bodies or a surface pressure far outside human tolerance. The star itself must be understood again from close range. A distant star's brightness and spectrum provide important information, but arrival allows more precise measurement. The ship observes stellar activity, ultraviolet output, particle storms, magnetic behavior, and long-term variability. Red dwarf stars, which are small and cool compared with the Sun, are common and can host planets close enough to receive warmth. Many red dwarfs show strong flares, especially when young. Observations indicate that stellar activity can affect planetary atmospheres. It remains uncertain how many worlds around such stars can keep stable, life-supporting conditions over long times. The planetary system may contain more hazards than expected. Dust belts, asteroid belts, comets, moons, and rings can occupy regions near planets. Small bodies may be hard to detect from interstellar distance. Their orbits matter for safe approach, resource use, and collision avoidance. A ship that has crossed light years still must navigate local debris carefully. Arrival does not end navigation. It changes navigation from a long straight uncertainty into a crowded gravitational problem. If a candidate planet has an atmosphere, the first question is not whether it looks like a sky. The question is what the atmosphere contains, how thick it is, how it moves, and how it changes. Oxygen in an atmosphere may suggest biological activity on some worlds, but oxygen can also arise through non-living processes under certain conditions. Methane, carbon dioxide, water vapor, nitrogen, sulfur compounds, and aerosols all require interpretation. An aerosol is a suspension of tiny particles or droplets in gas. Remote readings can be ambiguous. Close probes and orbiting instruments must test the air before any human exposure. A world with life would create deeper caution. Alien life, if present, may be microbial, biochemical, and difficult to recognize at first. It may not use the same molecules as Earth life, or it may share some broad chemical patterns because chemistry limits what life can do. It remains unknown whether life exists beyond Earth. If life is found, contact carries scientific, ethical, and biological concerns. Native organisms might be harmless to humans because they evolved separately. They might also produce toxins, reactive compounds, or ecological effects that are dangerous. Human microbes could also harm native ecosystems. The presence of life makes settlement more complex, not simpler. A world without life is not automatically safe either. Its soil may contain perchlorates, heavy metals, reactive dust, or sharp mineral grains. Its atmosphere may lack oxygen or contain toxic gases. Its surface may be exposed to radiation if the planet has no strong magnetic field or thick atmosphere. Its weather may include extreme winds, corrosive clouds, global dust, or temperature swings. Its water, if present, may be buried, salty, acidic, frozen, or chemically bound in minerals. Every useful resource must be located, extracted, purified, and protected. Gravity shapes the future. If surface gravity is much lower than Earth's, long-term human health may remain uncertain. If it is much higher, movement, childbirth, construction, and circulation may become difficult. A planet can offer open land and still impose biological strain. The ship's people may have lived under artificial gravity for generations, and their bodies may be adapted to that environment. A planetary surface is not merely a destination, it is a new stress. Landing is also not simple. A generation ship may be too large to enter an atmosphere or land on a surface. It may remain in orbit while smaller craft descend. Those craft require heat shields, propulsion, guidance, landing sites, and return capability if needed. A thick atmosphere creates heating during entry. A thin atmosphere gives little braking. No atmosphere requires full powered landing. Each descent uses equipment that must work after a long voyage. Each failure can cost lives and materials that cannot be replaced easily. Settlement begins with dependence, not freedom. Early surface habitats need sealed air, water processing, power, radiation shielding, food production, medical care, and waste recycling. In many cases, the first settlement may resemble the ship more than Earth. It may be underground, covered with soil or ice, or built inside pressure vessels. The horizon may be visible, but breathing may still depend on machines. The sky may be real, but unsafe. The ground may be wide, but chemically hostile. Reaching a planet does not remove the need for life support. It only changes where life support stands. The ship itself becomes part of the decision. It may remain the safest habitat, the main factory, the archive, the hospital, and the source of spare parts. Dismantling it for materials can support settlement but reduce safety. Preserving it can protect continuity but require maintenance in orbit or local space. The population must decide how much of its old world to keep and how much to transform. This decision is technical, social, and emotional. The dark side of arrival is that the end of travel may not be the beginning of a home in the familiar sense. A star system can be reached and still resist settlement. A planet can be promising and still require generations of work before it supports ordinary life. The people who arrive may not find oceans, forests, or breathable air. They may find rock, ice, radiation, and chemistry. The voyage across interstellar space ends at a real place. But reality is narrower than hope. Arrival closes the distance, then opens the final uncertainty. The ship rests within the reach system, no longer between stars, yet not released from care. Its walls still hold air, its farms still need light, its people still move through rooms shaped by old decisions and new measurements. Outside, the destination world turns under its own sky, known more clearly now, but not made gentle by being near. The long voyage leaves no simple victory. It leaves records, worn materials, repaired systems, changed language, remembered names, and children who know the ship and the new star together. The dark side of interstellar travel remains present in the quiet truth that distance can be crossed without removing dependence. Life still needs protection. Knowledge still needs renewal. Trust still needs tending. In time, some may descend, some may remain above, some may study the planet for years before choosing where to build. The first shelters may be small, sealed, and careful. The first crops may grow under lamps beside soil from another world that must be tested again and again. The first open view may be beautiful, but beauty does not make air safe. The generation ship becomes a bridge between origin and arrival. It carries the memory of Earth, the labour of the voyage, and the uncertain beginning of settlement. Its journey shows that space is not empty of consequence. It is cold, thin, patient, and exact. Human survival within it depends on humility before matter, time, biology, and choice. The final boundary is quiet. A star shines nearby. A world waits below. The vessel remains awake, holding life a little longer, while the future begins slowly, carefully, and without certainty.